Hello everyone, and welcome to my channel. This is an educational channel. We take deep dives into some of the great theories of everything that I've come across in my research. And today is our 457th video on the reciprocal system of theory. If you're keeping track at home, but even if you're not, don't worry, we won't be doing the reciprocal system forever. We're going to get into a whole lot of other great subjects, but we want to lay the groundwork here for the reciprocal system, as it and the tree of life are kind of my foundations, and then I get into a whole lot of other subjects that also tie into those core subjects. So we'll probably stick with the reciprocal system for a little bit longer. Then we'll move into some quantum arithmetic, some synergetic geometry, some music theory. We've done a little bit on nutrition and health and exercise, and we'll do some history, some ancient and modern history, and it'll be great. But for now, let's take a look at the work of Dewey B. Larson, the author of The Reciprocal System. In 1959, he proposed his two fundamental postulates, which were two sentences about how he believed the universe operated. From there, he derived a theoretical universe about what the universe would look like if his postulates were correct, and then compared his theoretical universe with the empirical universe of the scientists. In today's video, we're going to look at his book called Basic Properties of Matter, Chapter 7, Temperature Relations. And this whole book is on chemistry primarily, and he compares his results. He derives equations for many of the basic properties of matter and applies them to pretty much all the elements, maybe not the radioactive ones, but all the at least common elements and hundreds, if not thousands, of other compounds, and then compares them with the tables that have been established by the legacy scientists. And Larson's reciprocal system is otherwise known as the universe of motion, because he attempts to build his universe upon motion. The first postulate reads that the universe is comprised or composed of one component, motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. So there are really like 4 assumptions built into that. And then the second postulate is just more really having to do with what scientists agree to a priori. The universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Some of Larson's followers have rejected parts or all of that second postulate and gone into some of the more exotic forms of geometry and mathematics. But the basic idea behind it is just that math works, geometry works, logic works, and we use those things to derive our theories. And so he's taking his first postulate and he's using it to derive his theoretical universe. And he uses the principles of mathematics and geometry and logic to do so. So the first postulate is where the main thrust of the reciprocal system is. And those 4 assumptions: the universe is made out of motion. Motion is the relationship between space and time. Space, time, and motion come in 3 dimensions. Space, time, and motion come in discrete units only. And he goes from there. Now, when Larson is referring to motion, he's referring specifically to a more generalized kind of motion that he calls scalar motion. This scalar motion is a motion that has a magnitude, but it has no specific direction. It's kind of like a more flexible kind of motion because it doesn't have a direction. You can envision a scalar motion if you take a balloon and you put dots on it and you blow up the balloon. All of the dots will be moving away from each other. If you want to fill in another dimension of that, you can take some raisin bread and put it in the oven, and all of the as the oven heats up and it rises, all of the raisins will be moving away from each other. But they won't be moving in any specific direction. All of the dots will be moving away from all of the other dots. Every dot will be moving in every direction. So there is no specific direction. And in Larson's universe, he also posits basically 4 kinds of motion. You can have a translational motion. You can have a rotational motion. You can have a vibrational motion. And you can have a rotational vibration. And you can have these in 1, 2, or 3 dimensions. And a scalar motion can become any of those. You can have, so a scalar motion is a flexible thing that you can, it can transform into all of those different kinds of motion. But it is a physical motion. You can see it in real life with your expanding balloon, and the astronomers have viewed it through their telescopes. Hubble observed way back almost 100 years ago that all of the distant galaxies were receding from us. They were all moving away from us. And unless we want to take the geocentric 15th century geocentric view that our galaxy is at the center and everything is moving away from us, then we would have to assume that our galaxy is also moving in this manner away from everything else in all directions. So at least as far as the largest, heavenly bodies, the galaxies, they're all participating in this kind of a scalar motion. Now, the reciprocal system is known as the reciprocal system because of the reciprocal relationship between time and space in motion. Time and space do not exist in and of themselves. They only exist together in motion. And motion is basically a fraction with space or time as the numerator and time or space as the denominator. You can see this in speed. The bike is going 12 miles an hour. That's 12 miles of space in 1 hour of time. That is space over time. That is speed. And there is a reciprocal relationship there. If you double the speed, you can say the bike is now going 24 miles an hour. Or, equivalently, you can also say the bike is now going 12 miles per half hour. You can multiply the space or you can divide the time. It doesn't matter. They are equal. And so that is a reciprocal relationship between space and time in speed. But Larson extrapolates and he applies that to all scientific phenomena that he equates to motion. So matter is a kind of motion. And energy is a kind of motion. Matter is space. Matter is time to the third power over space to the third power. Energy is time over space. Acceleration is a kind of motion. It is space over time to the second power. Force is a kind of motion. It is time over space to the second power. Pressure is a kind of motion. It is time over space to the fourth power. Power is a kind of motion. It is simply 1 over space. And so all of our scientific phenomena are forms of motion, and they are relationships between space and time, which is very handy if you're trying to, figure out your validity of your equations and your units, because the MKS system uses 3 variables, including matter. But now you can get rid of the matter and turn it just into space and time only. Now, when you have that expanding balloon, you can also reverse the order of that, of the direction, the scalar direction of that expanding balloon, and contract it. You suck in the balloon, suck in the air, and the balloon contracts. All of the dots will be moving toward each other. This is the outward movement of that balloon is called the progression. The inward movement is called gravitation. So matter basically is the result of taking that outward movement of the progression and reversing it. All matter gravitates. So everything that's on the surface of that contracting balloon is, or all atoms, all forms of matter are on the surface of that contracting balloon. They are all moving inward toward each other. It appears as if there is a force field, and that gravitation is an attraction between 2 bodies, but it isn't. Larson calls this an as-if force. It behaves just as if it was one body was attracted by another body. But in reality, that's only the result of assigning a reference point. So if you decide to take one of those dots and say, this is my reference point, this dot will from now on will be assigned as motionless, and all the other dots will appear to be attracted by that reference dot, and there will appear to be force fields between all the other dots and your reference dot. But that is only the result of assigning the reference point. All of the dots are moving on their own. All dots are moving toward all other dots. There is no force field. There is no attraction at a distance or anything like that. Every dot is following its own course, and its gravity is intrinsic to it. And so that outward motion transforms into this inward motion by reversing it. And again, it has to be done in 3 dimensions. This is the 3-dimensionality. Motion, space, and time exist in 3 dimensions. So this outward motion of the progression has got 3 dimensions to it. You can also see this 3-dimensionality in, now these are, once you actually have a gravitationally bound system and you are abstracting, then you have this coordinate space and clock time that Larson calls this the spatial reference system. So, and there is also a corresponding and reciprocal temporal reference system that is coordinate time and clock space. So you have 3 dimensions of space in a still frame in our environment, 3 dimensions of space in a still frame, a spatial background, and we are unfolding through time. Time is getting later and later and later. The flow of time, or the progression of time, which is a scalar motion. Time is not flowing in any specific direction. It's just getting later and later and later. And in a reciprocal environment to ours, there is a three-dimensional time, which again is anathema to science, but part of Larson's theory, a necessary part of it by the reciprocal postulate, that there is somewhere in the universe where there's three dimensions of time in a still frame, and space is a scalar property that is always getting further and further and further apart. Larson calls that the temporal reference system. Okay, now we have this discrete unit postulate, and that is saying that space, time, and motion all come in discrete units only. You have to have a full unit of space before you have space. You have to have a full unit of time before you have time. And if you have 1 unit of space in 1 unit of time, space over time being speed, you have what Larson calls unit speed. And unit speed is also known as the speed of light. This is the speed of the progression. The progression is always moving outward at 1 unit of space per 1 unit of time, or the speed of light. So this is our empty universe. This is what we have when we have nothing in the universe, is that we have outward motion at the speed of light at all times, in all places, or all locations. And so this is really like the expansion of space and the expansion of time. It's coming from kind of from everywhere. It's omnipresent, eternal. It's an ether or a 0 point. Larson calls it a null point or a neutral point. This is what's always there, and this is what Larson calls the progression of the natural reference system. And so this is the natural reference system. We have a stationary spatial reference system, a stationary temporal reference system. These are kind of, especially the spatial reference system is where scientists make their measurements from. But Larson switches that over, and he takes his measurements from the natural reference system, which is a moving reference system. Everything is always moving outward at the speed of light in all directions. And Larson takes his measurements from there. Now, you can take your measurements from the stationary reference systems, but you have to recognize that you're doing that, and that these are abstractions, and these are for convenience, to be able to make measurements. But this is not how the universe operates. Okay, and also with this progression of the natural reference system, this basically means that half of the universe is moving slower than the speed of light, and half of the universe is moving faster than the speed of light. The speed of light is the boundary between these two separate regions that Larson refers to as the material sector and the cosmic sector, respectively. And in the material sector, you have coordinate space and clock time, and in the cosmic sector, you have clock time. You have coordinate time and clock space. And within each one of these regions, you have also a sub-region that, in the material sector, both have to do with the discrete unit postulate. Units of space in the material sector. If you don't have a full unit of space, say you have 2 atoms that approach each other and they get to 1 unit of space apart, which is 2 millionths of an inch approximately, then they can't move any closer together because you don't have less than 1 unit. They have to stay at that 1 unit distance apart. But what they do in order to, keep moving closer together, so to speak, as if they were moving closer together, is that they now move outward in time, which is, by the reciprocal postulate, the equivalent of moving inward in space. They are not moving in space, but to us, it appears as if they are, because we are bound to a spatial gravitational system. And so we only see space, we don't see time. And so when they actually move in time closer together, we see it in equivalent space. And there are some adjustments that have to be made having to do with our perceptual abilities in order to actually really see what's going on there. But we don't see in time, we see in equivalent space. And again, that's a second power relation, and it also has to be reduced by the interregional ratio. Anytime that we cross a boundary in the universe, the rules flip and our perception is somewhat distorted. Now, there is a corresponding space region in the cosmic sector. So in the material sector, you have a time region within the unit of space. In the cosmic sector, you have a space region within the unit of time. And these are the realm of interaction of atoms and molecules, which is the subject matter here for his chemistry reading. Now, the last thing that I'll say is that in Larson's system, the periodic table is based on all atoms are combinations of motion. First, you have to reverse the progression, and then you have to rotate it back, basically in 3 dimensions. So there are 3 numbers of the periodic table of each element for Larson. And those are the numbers that he uses to figure out his equations for the basic properties of matter. Also, the rules invert when you cross into the time region. Now the progression is outward in time, or inward in equivalent space, and gravitation inward in time, outward in equivalent space. So the directions of those 2 major forces invert, and where they are equal, the progression is omnipresent and eternal and always the same. Gravitation is based on an inverse square law. So there is a point where they are equal, and when they are equal, that is where atoms, groups of atoms can establish a force equilibrium. So this is really like the interatomic distance. And he goes from there. So let's read some of his stuff here from chapter 7 on temperature relations. You might not get much, if any, of all of these, but again, this is like detective work. You want to just try to piece together what you can, pick up a breadcrumb or 2 and add it to what you already know, and you'll be astounded how many epiphanies you have and how much you're able to put together over time. In the theoretical minimum situation where the effective thermal factors are 1, 0, 0, and again, those are basically the 3 numbers that Larson uses for his elements, and the scalar sum of these factors is 1 unit, the temperature of the initial negative level is 1 unit out of a total of 128 that correspond to the full 510.7 degrees temperature unit of the condensed states. Now, Larson's major thrust here in determining temperature is that each atom or group of atoms, whether they form a tight-knit group or whether they are on their own, temperature is measured atom by atom or molecule by molecule. It's not a measure of like the whole group of them together. Each thermal group, each molecule has its own temperature. But since the thermal motion is effective in only one direction, the ratio becomes 1 over 256. There are really 128 directions or orientations within the time region, but thermal motion is only outward. thermal motion goes along with gravity, whereas compression goes along with the progression. And so the thermal motion is basically like an intermittent outward force. And so that's why you have to divide it by 2 again. And the 0 point temperature, T sub 0, the temperature at which the thermal motion counterbalances the negative initial level of vibration, which is basically the 2 photons at the core of all of the atoms, is 1.995 degrees Kelvin. For a substance with thermal factors A, Z, and Y, the normal 2/9 initial specific heat level, we then have T sub 0 equals 1.995 times the quantity A plus Z plus Y degrees Kelvin. So that is his equation for T sub 0, which is the initial temperature. That's the temperature at which the atom has balanced out the initial negative level of the photon. Now, I hate to tell you this, but it probably took me like 15 years to figure out that paragraph. I still haven't figured it out completely. But, you know, so sometimes Larson skips a step or two and just leaves you hanging. You just have to do the best you can. Larson was one guy, and he was set with a gargantuan task, and it's you know, absurd to expect anybody to make everything crystal clear for you. You know, when you're the originator of a theory, he has to come up with a whole new language. He has to come up with whole new concepts. So it's up to people like me and you to, you know, build this thing and to make it more accessible. You know, the originator of the theory can't do everything. Okay, this value, especially since he's been dead for 34 years now, this value completes the definition of the specific heat curves by defining, and again, specific heat is the amount of heat that is necessary to raise a certain amount of matter, a certain amount of temperature. So it's really like the rate of heat efficiency. This value completes the definition of the specific heat curves by defining the temperature scales. So that's what he was doing. He's defining the temperature scales. So each one of these atoms is on its own specific heat curves. The inflections of the curves, they're really just a bunch of straight lines, but the inflection points of the curve represent different places where the atom undergoes a transition. For one reason or another, there are really 2 kinds of transitions. The first order transitions have to do with the crystal structure, or really the, you know, so-called bonding of the atoms. How are they packed together? The packing, the geometrical packing. They can be, you know, the hexagonal close packing, or it can be the face-centered cube, or other kinds of geometrical packing. And then the second order transitions have to do with changing the amount of rotational factors that are involved in the process of heating. And so whenever another set of factors comes in, it drastically lowers the efficiency of the heating, and so the curve becomes more vertical as we move along, because statistically, heat is going to the atom wants to stay in the solid state as long as possible, because statistically it is more probable. There's less energy involved for an atom in a low energy environment to want to stay in that environment. And so the atom makes every kind of adjustment that it possibly can make to avoid heating up and getting close to or over that melting point. Okay, so each atom has its own curve, but Larson is defining the temperature scale, so he's basically coming up with a common denominator for all of these different curves. It will be more convenient, however, to work with another of the fixed points on the curves, the first transition point, T sub 1, as this is the unit specific heat level on the initial linear section of the curve, while T sub 0 is 2/9 of a unit above the initial point. Okay, so T sub 0 is 2/9 above, which is the photon. The photon is negative 2/9 for reasons that would take me several minutes to explain. But I've probably explained it on a different episode somewhere, and I'll do it again at some point. But T sub 1 is a unit. So naturally, T sub 1 is going to be 9/2 of what T sub 0 is. And so that's what he comes up with here. While T sub 0 is 2/9 unit above the initial point. The temperature of the first transition point, therefore, is 8.98, which is 1.995 times 9/2. So T sub 1 is 8.98 times the quantity A plus Z plus Y degrees Kelvin. Okay, we're going to conclude it right there. I'd like to be moving through this faster, but there's just kind of too much background information here to be able to, present anything coherently. And again, that's the problem with Larson. I think his main error is that he was writing for a scientific audience, and he at least in retrospect, I think you can kind of see that the scientists are the last people that are going to get on board with this. He should have written for lay people, and if he would have done that, he would have had to clarify things a lot more for a lay audience. But scientists are generally offended by the reciprocal system. It takes a very open-minded one to even give it a second thought. Okay, thanks for tuning in.